All right, here we go, guys. This is a big day. If you hear about anyone who's taken calculus or you've ever heard them talking about it, you probably heard them mention something about derivatives. And today we actually get to what a derivative is. It's closely related to what we've been doing the last couple days. So just to recap that, what we've been doing to find the slope of a curve at a point, or the slope of the tangent line at a specific point, and that point being x equals c, some number there. Here's what we've been doing, right? We've been setting up the slope between f of c, whatever that x value was that we wanted the slope at, f of c plus h minus f of c over x, c plus h minus c, which always left you with h, right? This was just a representative of the slope, and then taking the limit of it as h approached 0, right? That's what brought those 2 points infinitely close together to give you that tangent line slope. Okay, so this setup gave you the slope at whatever x value you wanted, c in this case, we're calling it. So the idea here is, well, what if I want the slope at several points on a function? Do I have to do this setup, from scratch every single time? Why don't I generalize the process and do it in terms of x, the variable x? And that's what a derivative is, basically. It's doing this. Here's the limit definition for it. It's doing the same procedure, but instead of doing c plus h, because you want the slope specifically at that number, we generalize it and we leave x in there. F of x plus h minus f of x, leaving the variable x in there over h. And I take the limit of that as h approaches 0. And if you remember doing these earlier in this chapter even, and in previous chapters, what you get out will have x in it. Your answer to it is an expression that contains x. And that expression you get out is what's called the derivative. It's a function, and it's a different function, but it's derived from an f of x. So it's called the derivative of f of x. And to denote that it comes from f of x, but yet it's a different function altogether, they put this apostrophe here, read as f prime of x, f prime of x. So what a derivative is, it's a function. I mean, generally you can think of it as like a slope function, but it's a function that can be used to give you the slope of a line tangent to a curve, or the slope of the curve itself at any given x value. So here's what I mean by this. Here's the example we're going to do, and if I wanted to find the slope at all these given spots, x equals 0, x equals 1, x equals 3, x equals 5, I could do it one at a time and do this whole limit procedure 4 separate times, or I can just do this one limit procedure once to get the derivative. And then I can use that derivative, and you'll see how we do it. So first things first, part A, find the derivative. Okay, so notation in calculus is big, so I've been trying to harp on it, but definitely try to be good with it. What we're doing here is we're finding f prime of x. So I almost like to start it off like it's a complete sentence. F prime of x equals, and we're doing the limit as h approaches 0 of f of x plus h for this specific function. Now remember, f of x plus h, that part might take you a little work. Maybe you like to simplify that off to the side before you jump into the limit. But for this function, f of whatever means to plug that in for x. So hopefully you're good with these, because we've been doing them. So now that we need it for something, hopefully the mechanics, the algebra of it just kicks in. But if I'm doing f of x plus h, I'm plugging x plus h there, x plus h squared minus 6 times x plus h, and then I'm going to subtract 7 from it. If you want to simplify that off to the side, that'll be x squared plus 2xh plus h squared minus 6x minus 6h minus 7. I know I got a little tight in there, a little squeezed in there. No like terms to combine there. So all of that is the f of x plus h part of the limit definition of this. So f of x plus h, we take that whole thing, x squared plus 2xh plus h squared minus 6x minus 6h minus 7. And then we have to subtract f of x. So subtracting f of x is subtracting this entire function. Now remember, subtracting that entire function means you got to distribute the negative to it. So minus x squared minus negative 6x becomes plus 6x, minus negative 7 becomes plus 7. And now we're off and running with the algebra. As you remember, everything that doesn't have h should cancel out. So make sure that it does, otherwise you've done something wrong and maybe you can catch yourself. X squared minus 6x plus 6x minus 7 plus 7. Good. Now look at the terms we're left with. Don't overlook any because they're all kind of crammed in there. You've got 2xh plus h squared, and right in there you've got a minus 6h, and that's it, all over h. So we're going to factor h out of all that, or if you like, you can divide h and cancel it away. If you can do that mentally, just be careful you don't miss anything. But if we factor h out of there, it will be a 2x plus h minus 6 all over h. The h cancels, which means now that that is gone, you can now plug 0 in for h. Remember, you haven't done the limit until you plug 0 in for h. And when you plug 0 in for h, you'll be left with 2x minus 6. This is f prime of x. That is the derivative. It's a function that was derived from this function. And now let's see how to use it. Okay, the derivative to find the rate of change of f of x. This is f of x, the parabola x squared minus 6x minus 7. You could find its intercepts and all that if you don't believe me. But if I wanted to find the rate of change, aka the slope, at specific points, at x equals 0, and just for visualization, at x equals 0 is right here on the graph. And finding the slope of the curve or the slope of the tangent line, I can see that it's definitely going to have a negative slope. But what is it exactly? I'm going to plug 0 into this function. Now, this is where you really want to, try to be better about your function notation in calculus. If you're doing a plugin, try to show that plugin always with proper notation. F prime of 0 equals, and if you want to do that part in your head, I don't really care. But definitely your teacher's going to like you to be communicating with function notation. It's very big in calculus. So I'm going to this derivative and plugging 0 in for x. And what I get out from this, that's the slope of that line. At 0, the slope is negative 6. And when you learn the language of calculus, that sort of becomes second nature. The derivative of 0 is negative 6. That means the slope at x equals 0 is negative 6. Pretty cool. And now let's just try a couple others here. What about the slope at x equals 1? No problem. I can just keep using this same function here. So f prime of 1, plug 1 into that. 2 times 1 minus 6, and you get 2 minus 6 is negative 4. Notice at 1 here, it's always good to keep visualizing these concepts you're finding. That's a big part. At 1, it's still got a negative slope, but it's a greater negative slope than this one. It's less steep, if you want to say. It's starting to approach, starting to flatten out. Starting to approach this vertex. At x equals 3, you want the slope? No problem. I plug it right into this derivative. So this is why it's beautiful. You do one big limit, and then you've got this function, and you can use it to find as many slopes as you want on that one specific curve. So 2 times 3 is 6. 6 minus 6 is 0. And this is an interesting idea here that the slope is 0. So that should tell you this point is where specifically on the curve. 3 is right here, and that tells you that is the vertex of the curve, because that's the only spot on the curve where the slope should be 0. a horizontal tangent line. Everywhere else is going to have either a negative slope, or to the right it's going to have a positive slope. So right there. Or maybe in physics you learned about an object being launched upward, and at the very top its velocity is 0 before it comes back down. Similar idea. A lot of physics in calculus next year, a lot of overlap. You want the slope at 5, and that's going to be over here, 4, 5. That would be right about here on the curve. Definitely going to be some positive slope. What is it exactly? Hey, just go to this derivative function, plug 5 in. 2 times 5 minus 6, that's 10 minus 6, that's 4. The slope at 5 is 4. Very nice. So finding the derivative, doing this f of x plus h and keeping it in terms of x, and then using that to get the slope at any point you want. So that notation, f prime, f with the apostrophe, or if you were doing g of x, it would be g prime, or h of x will be h prime. And you will have problems next year where there are multiple functions in the same problem, so notation is important. If your function is just called y equals, as many equations are, well, one way is to just, fine, call that y prime equals instead of f prime. But you should also notice this notation, and for right now you don't have to absorb it too much, but this notation, called the Leibniz notation, named for Leibniz, another mathematician with Newton who kind of developed a lot of the ideas of calc. This is dy dx, or dy over dx. That means the same thing as y prime equals, but here was his idea of that notation. If you look at what it is, it should make sense, because it's saying the difference in y over the difference in x. And specifically, dy means like the infinitesimal difference in y over the infinitesimal difference in x. And that's what slope is, right? Difference in y over difference in x. So I like to just at least talk about that. It becomes very important next year, but it's at least nice to at least recognize that right now, that hey, that means the same thing as y prime. It's the slope, that's what y prime is. For this, now let's find the derivative, no problem. Y prime, or dy over dx, equals, I'm going to do the limit as h approaches 0 of f of x plus h minus f of x all over h. And for these ones, although they're fractions, f of x plus h, remember, is really a little bit nicer here because there's nothing to expand. You're just replacing x with x plus h minus f of x, which would be 1 over x minus 2. And then it's one of these complex fractions. Make common denominators and put them together. Multiply top and bottom by LCD, however you like to do it. Don't be lazy. If you're multiplying by the LCD, then write it in the top and bottom, because otherwise, if you only write it once, that means you'd only be multiplying the top, and that's not good. Distribute, simplify, these kinds of things are probably pretty easy for you by now if you've been doing the work, the mechanical part of this. Distribute this, x plus h minus 2 is going to be canceled. You're going to be left with x minus 2 times 1. And then here, distributing this to this fraction, x minus 2 is going to cancel, leaving you with negative 1 times x plus h minus 2. Negative 1 times that, you distribute that negative 8x minus h plus 2. And of course that should happen that way, because now x minus x cancels, negative 2 plus 2 cancels. The only thing you're left with is negative h, which means I can cancel it with that h right there, leaving you with just a big fat negative 1 up top. All that stuff canceled out. That h canceled, which means I can now plug 0 in for h here. So just be careful. Got negative 1 on top, and when I put 0 in for h, you'll have x minus 2 times the other x minus 2, and that's x minus 2 squared. If you want to FOIL that out, be my guest, but you'll find your teacher will probably leave it as x minus 2 squared. And that thing is y prime, the derivative. And now we're going to use it to find the slope. Here is this graph of y equals. Equals 1 over x minus 2. Just notice these little properties that you should know. There's a vertical asymptote at x equals 2, because that's where the denominator is equal to 0 at x equals 2. There's an HA at y equals 0, because the degree of the bottom is bigger than the numerator. The graph is flattening out. And now we're going to use this to find the slopes at whatever points we want. If I want the slope at x equals 0, you can use y prime the same way you do f prime or g prime or f of x notation. It hasn't often been done in your math career prior to now, but it'll become second nature to you. Y prime of 0, mean I'm plugging 0 into y prime. And when you plug 0 into there, you'll have negative 1 over 0 minus 2 squared. That'll be negative 1 over negative 2 squared is positive 4, negative 1/4. And if you look on this graph, that means when x is 0 on this curve, that's one specific point right there, at that spot, that slope of that tangent line, or the slope of the curve, is negative 1/4. Very flat, but definitely a negative slope. You want the slope at x equals 3. Here's where we are on the graph, 1, 2, 3. We're right there. That should definitely be a negative slope also. How negative? Well, let's see. Y prime of 3, negative 1 over 3 minus 2 quantity squared. 3 minus 2 is 1. 1 squared is 1. Negative 1. And so there we are. That slope is negative 1. It looked like a smaller, technically that's smaller, you know, when you're talking negatives. Negative 1 is smaller than negative 1/4. It looked like a smaller slope. And y prime of 5, finding the slope at 5. Now, 3, 4, 5, here's where we are. We should have a sense of what this is going to be. It should definitely be negative, but I definitely think it should be, you know, greater, closer to 0 than negative 1. And so y prime of 5, I'm going to plug 5 into this derivative. Negative 1 over 5 minus 2 squared. 5 minus 2 is 3. 3 squared is 9. Negative 1/9. And there we go. Very small slope, or actually greater than these ones. Very close to 0, but still negative. Part C says, write the equation of the line tangent to the curve. Okay, so tangent lines at a specific point. Just remember you need two things. You need the point and you need the slope. The point is just getting the y-coordinate. So remember, the y-coordinate just comes from plugging it into the regular equation. So that would be plugging it into this equation. You know, at 1, if we want to look here, at 1 we're talking about that specific point on the curve. So what is y of 1? 1 over 1 minus 2, and that will be negative 1. So our point of tangency is 1, negative 1. That seems to make sense with that graph. And now we need the slope at that spot. The slope at that spot, that's what I'm going to use the derivative for. So y prime of 1. Getting the slope at 1 means using the derivative function at that value. So negative 1 over 1 minus 2 squared. And you get negative 1 again, actually kind of boring that we got the same value, but whatever, it's going to happen from time to time. And so the equation of your tangent line, you can use any form you want, but I'm using point slope form. Y minus the y-coordinate is y plus 1 equals the slope times x minus 1. And yes, if you want to write negative 1 there, that's fine too. Good. And the last question here, and by the way, a great way to check this answer is to use Desmos or your graphing calculator and graph the original function, and then to graph this line. And you should see the line just perfectly glances off your curve right at that spot. And if you use the intersect feature or you click on the point of intersection on Desmos, you should see that point is 1, negative 1. And here's just sort of a thought here. Are there any points on the graph which have a horizontal tangent line? And a horizontal tangent line means this should, you know, any tangent lines where it's perfectly flat. Just think, a derivative gives you slope, right? And a horizontal line has a slope of 0. Is there anywhere on here that the slope is perfectly 0? And if so, how many places? Like on the front problem, there was one point at the vertex where the slope was perfectly 0. And so what you would really do, you might be looking at the graph and just trying to eyeball it and saying, as I go in this direction, the slope is approaching 0. And as I go in this direction, the slope is approaching 0. But if I really want to know if it ever equals 0, I will take my derivative. And you will just set it equal to 0. Are there any x values that when you plug them in, make the whole fraction equal to 0? And hopefully you really see that no, the fraction's only equal to 0 when a numerator is equal to 0. So no matter what you put in for x, this fraction will never be 0. This has no solution. That means there are no horizontal tangent lines. But that'll be kind of a recurring problem in calculus that you find when something has a horizontal tangent line by setting its derivative equal to 0. All right. There's a lot of ideas to unpack there in one day, but that's a big day, so we're going to practice with that. Please ask questions if you have any, and hopefully this made sense. Good luck, kids.